So this presentation is going to be on 7.4, calculating the equilibrium constant. And basically what we're going to be doing is we're going to be calculating K from concentrations or partial pressures of reactants and products for a reaction at equilibrium. Why are these problems giving us temperature and specifically saying that these reactions are happening at a certain temperature? So this is basically because KEQ values are going to be calculated at specific conditions and at specific temperatures, and temperature is going to change the KEQ value. However, we do not need the temperature to calculate KEQ, but if it does change, our value of KEQ is going to change. So basically, they're probably going to give you the temperature in the problem, and then they're probably going to give you a KEQ value at that specific temperature. You can just kind of ignore it. You don't have to worry about the temperature, but if it does change, know that the KEQ will also change. So let's go ahead and look at an example FRQ. So we have a reaction X plus Y2 gives us XY2. For the reaction given above, a system at 298 Kelvin has the following partial pressures at equilibrium in 3 separate experiments. So it gives us experiment 1, experiment 2, and experiment 3, and it gives us the partial pressures of the reactants and the products in those experiments. So it says write the equilibrium constant expression Kp for the reaction given above. This is exactly like what we've been doing. You're just going to write the Kp for the reaction, and so remember that's going to be products over reactants. And so what you're going to do is you're going to write Kp equals the partial pressure of xy2 divided by P of x times P of y2. And so then it's asking us to calculate the value of Kp at 298 Kelvin for each of the 3 experiments. Notice the temperature is the same, so we can ignore it. And it's asking us to do it for each of the 3 experiments. So for experiment 1, what you're going to do is you're going to plug in 2 atmospheres for P of x, 5 atmospheres for P of y2, and 1 atmosphere for P of xy2. So this is just simply a plug and calculate type of problem. And so when you plug those in, for trial 1, you should get 1 divided by 2 times 5, and so that's 1 divided by 10, which gives you a value of 0.1. Notice how I didn't write any units here because our equilibrium constant doesn't have units, so we don't have to worry about tracking them. Okay, if we're going to do the same exact thing for trials 2 and 3, again, you're going to just plug these values into your expression that you wrote in A, and it becomes a pretty simple problem, and you should get for trial 2, 2 divided by 2 times 10, which is 20, so 2 divided by 20 gives us a value of 0.1 as well. And for trial 3, we're going to use 0.5 divided by 1 times 5, and so then that gives us a value of 0.1 as well. Notice, since we didn't change the conditions at all, that the Kp for all 3 trials is exactly the same. This is because in equilibrium, everything is going to remain constant. It's the concentrations are remaining constant, the pressure ratios are remaining constant, so this is why we're getting the same value for all 3 trials. Let's go ahead and look at a different example. So in this example, it wants us to find the Kp at 500 Kelvin, and it gives us the initial concentrations of our CO2, our H2, our CO, and our H2O, and they're all in gas, so they're all going to have impact. So in this type of problem, when it's giving us the initial concentrations, what you're going to want to do is you're going to want to set up an ICE table. So an ICE table is going to be the initial concentrations. The C is going to be the constant that we're going to use to convert everything to each other. And then the E is going to be the at equilibrium. And so for this problem, it gives us all the initial pressures, and it also gives us the final pressure at equilibrium of H2O, and you can see that right here with that 3.40. So what we're going to do now is we're going to figure out how did we get from 3.20 to 3.40. And so when we look at that, we get that x equals 0.20. So we had to add 0.20 to H2O, and so that's how much was produced to get that final pressure at equilibrium. So when we're looking at our equation, I'm going to note that we have a 1-to-1 ratio for everything because there's no coefficients in front of any of our molecules with the balanced equation. So if that means that we are going to add 0.20 to H2O, that means that in a 1-to-1 ratio that we're going to add or subtract 0.20 from all of them because, again, the coefficients are all 1. So that means that we're going to add 0.20 CO, and then we're going to take away 0.20 from each of our reactants because this reaction is being driven forward. And so once we do that, we can get the final concentrations at equilibrium. And so we're just going to subtract 0.20 from 4.10, and you should get 3.90. And then we're going to subtract 0.20 from 1.80 to get 1.60. And finally, we're going to add 0.20 to 0 for their CO concentration and get a final equilibrium concentration of 0.20 of CO. And then once we do this, it becomes super easy because it becomes a plug and calculate type of problem now. Because now we have all of our equilibrium concentrations, so we just plug them into the equation. So again, I'm going to put my KP my KP equation right next to what I'm going to write down just so I can kind of see where I'm plugging in things. Now remember, it's going to be products over reactants. So for the partial pressure of CO, we calculated it as going to be 0.20. The partial pressure of H2O is 3.40. And then our two reactants are going to go on the bottom at 3.90 and 1.60. And so when we plug everything in, it looks like that, and we get 0.11 if you plug all of that into your calculator. And so that's our final KP. So let's go ahead and take a look at practice problem 1. So a graph of concentration versus time for the reaction AB gives us 2C at 295 Kelvin is depicted at right. This should look familiar, but we're going to ask a little bit different questions. So part A, write the equilibrium constant expression for Kc for the reaction. Again, this should be easy. Remember products over reactants and make sure that you're raising the concentrations to the coefficients. And so when we do that, we get Kc equals the concentration of C squared divided by the concentration of A times the concentration of B. Next, we're going to calculate the value of equilibrium constant at 295 Kelvin. Okay, so again, the temperature doesn't matter because the temperature is the same for the question and where we're calculating the equilibrium constant. So basically, this question is asking us to use the graph to determine the concentrations at equilibrium for each of the substances. So you have to know how to read the graphs. And so what you're going to do is you're going to have to figure out where equilibrium happens, and that's going to be where the lines level out. So it should be any time after t equals 20 or 20 seconds in the graph you can use because they all stay the same after that. And so the concentration you're going to use for your product, which is the C line, the yellow line, is going to be 0.4 molar. The concentration you're going to use for A is going to be 0.2 molar, and the concentration you're going to use for B is 0.3 molar. Again, I'm getting those values from the graph, and so you're going to see right here, C is at 0.4, B is at 0.3, and A is at 0.2. So if we plug those values in, okay, again, this is just a plug and calculate type of question. It should be pretty easy if you know how to read those graphs. Just to make sure that you're using the concentrations at equilibrium. So if you do that, you should get a value of 2.67. So now here's another practice problem, and this one's going to be a little bit trickier because there's a little bit more words. It doesn't give us a graph or a visual, and so we kind of have to sort through what's going on. So the compound BrCl can decompose into Br2 and Cl2 as represented by the balanced chemical equation of below. So it gives us a balanced equation. A 0.1 mole sample of pure BrCl is placed in a previously evacuated rigid 2-liter container at 298 Kelvin. Eventually, the system reaches equilibrium according to the equation above. calculate the pressure in the container before equilibrium is established. And so what we're having to do now is before equilibrium is established, we're going to have to try and calculate the pressure. And then part B, write the expression for the equilibrium constant KEQ for the decomposition reaction of BrCl. After the system has reached equilibrium, 42% of the original BrCl sample has decomposed. And then finally, determine the value of KEQ for the decomposition reaction of BrCl2. So there's a lot to work through in this problem. This problem isn't super easy. Let's go ahead and take it step by step. So for part A, calculate the pressure in the container before the equilibrium is established. So right now, we're going to want to use PV equals nRT. So the ideal gas law can be applied here because that's going to give us the pressure. If you notice, we're given moles, RT, and volume. And so we can kind of rearrange this equation to find pressure. And so if we do that, what we're going to do is we're going to get P equals nRT divided by V. And so that's going to give us the pressure in the container before equilibrium is established. And so if we plug those values in from the problem and remember our R, which is our constant, we get 0.10 moles times 0.0821 liters atmospheres over moles Kelvin times 298 Kelvin divided by 2 liters. Now, one thing that I am going to mention is that there are different constant values for R depending on the units that you need. These are given on your equation sheet, so you just have to pick the right R. It's not always going to be 0.0821, although that one's going to be the most commonly used because those are the most common units. But you're going to have to make sure that you're using the right R value to cancel out all your units because we want atmospheres. We want everything else to cancel out, which in this case, everything else does but atmospheres. And so when we make that calculation, we get 1.22 atmospheres. And so that's part A. Part B, write the expression for the equilibrium constant. So we need to write the expression. That's easy. Remember, products over reactants, they're all gas, so they're all going to be included. And remember, for that 2 coefficient for BrCl and the reactants, you're going to have to put it raised to the second. So we're going to write that, and it's going to look like that. So KEQ equals the concentration of Br2 times the concentration of Cl2 divided by the concentration of BrCl raised to the second. Now, the second part of this is a little bit trickier. So it says, after the system has reached equilibrium, 42% of the original BrCl sample has decomposed. So now, how do we go about doing this? Well, again, if we're trying to figure out or trying to calculate the equilibrium constant, we're going to try and do an ice table like we did in the previous slide. So I've kind of moved this over here so that we can kind of figure out and try and write it down. And so what we're going to use is we're going to use our initial pressure that we calculated in part A, and we are going to assume that there was no Br2 and Cl2 at the beginning. So we have our initial pressures. And so now what we need to figure out is we need to figure out kind of how these things are changing. So what we can do is that the pressure of the BrCl decomposed is 42%. So if we multiply that 42% times that initial 1.22, we know that 0.51 atmospheres has decomposed already. So if we subtract that out, 1.22 minus the 42% that's decomposed, that should leave us with the BrCl that's remaining. And so if we subtract that out, we get 0.71 atmospheres. And so that is going to be our X. And so we have 0.71 atmospheres. Now, let me go ahead and explain this minus 2x here, and then I'm multiplying that by 0.51. So the 2x is coming from the 2 coefficient in front of the BrCl. because we're going to have to multiply. We know that that's going to be, using the molar ratios, that's going to be 2 times what's going to happen to the Br and the Cl based on the molar ratios. So the BrCl is going to be 2x, and the Br2 and the Cl2 should only be x because of the molar ratios. And what we found was that 2x equals 0.51 because that's how much BrCl is decomposing. So if that's 2x, to find how much Br2 and Cl2 changed, we would have to divide that 0.51 by 2 because Br2 and Cl2 are increasing by half the amount that BrCl is decreasing. And so that's what's a little bit confusing about ice tables sometimes. And so when we divide that 0.51 by 2, we get 0.26. And so basically, each of the Br2 and the Cl2 are going to be decreasing by 0.26 based on the fact that BrCl was decreasing by 0.51 and it's decreasing at twice the rate as the products are. Okay, again, I got that twice the rate from the molar ratios, the coefficient in front of BrCl. So if we go ahead and add those to the concentrations that started at 0, you should get your final concentrations of 0.26. So now that we've filled out our ice table, what we can do is we can just easily kind of plug these into our calculations. And so when we plug it into our KEQ, you're going to get 0.26 times 0.26 divided by 0.71 squared, and you should end up with a KEQ of 0.13. All right, so here is practice problem 3. Go ahead and pause it right here, read the question, see if you can figure out the answer on your own. So here we're given a reaction 2HF gives us H2 plus F2. They're all in gas, so we know that they're all going to matter. And we have a 2 coefficient in front of the HF. So we need to make sure if we have anything to say about the equilibrium constant that we square that HF. So the reaction above is allowed to reach equilibrium at 300 Kelvin. In the same rigid container, the reaction is repeated at 500 Kelvin and the equilibrium constant K is found to be larger. All right, so we have a larger equilibrium constant. So our Kc is increasing. Which of the following best describes how the equilibrium concentrations of F2 and HF would be expected to change? Well, first off, let's go ahead and write our equilibrium expression so that we can visualize it and make sure that we don't get this problem wrong. So writing it, again, we got products over reactants, and we're going to make sure and square that reactant of HF because it has a 2 coefficient in front of the balanced equation. So now, how would we increase this Kc? So what we're trying to do is we're trying to increase this. And so if we think about it in math terms, to increase this number, we're going to have to increase the numerator or decrease the denominator or a mixture of both. And so if we have to increase the top to increase the number, that's going to be directly proportional. Okay, and if we have to decrease the bottom or the denominator to increase Kc, they're opposite. So if we decrease it to increase, that's going to be inversely proportional. So now what we're doing is we are looking for a number that makes sense in this. The reactants have to be inversely proportional. The products have to be directly proportional. So 1. H2 and F2 will increase because they are directly proportional to Kc, but HF will remain constant. All right, so half of that's true, but the other half is false. I'm going to go ahead. That's probably not going to be the best answer, so I'm going to go ahead and cross that out. H2 and F2 and HF will all increase because they are directly proportional to Kc. Well, I know HF is not going to increase because that's not going to help me, so I'm going to go ahead and cross that one out. All right, we got H2 and F2 will increase because they are directly proportional to Kc, but HF will decrease because Kc is inversely proportional to HF. Sounds right. Let's go ahead and double check 4 first, though. H2 and F2 will increase because they are directly proportional to Kc, but HF will decrease because Kc is inversely proportional to the square of HF. All right, so 3 and 4 sound very similar. They're both saying that the right things are going to increase and the right things are going to decrease. The only difference is this word right here, the square of HF. And if you look in our equation, we have to square HF. So what we're going to do is 4 is actually the better answer here. So 4 is going to be the right answer.